Okay, gang, here we're going to take a look at a few more examples. Now, we've been talking about area between curves. And so I think we only did one lecture or one example or maybe two the last time. Let's take a look at a few more. Okay, so here we have the identity function. Okay, and then the basic cubing function, all right, the basic cubing function. And the area we want to calculate is here and here. Okay, so find the area enclosed by these two curves. All right, so let's see. They're going to meet up at -1, 0, and 1. Next, I'm going to put my differential elements of area. Remember our very, very thin rectangles. So say maybe here. Okay, and as we did before, I'll label the top and the bottom of the rectangle. Okay, and then on the other side of the origin, maybe here, okay? Now, unlike the examples that we did in the previous lecture, notice here, gang, right? Remember we said think top curve minus bottom curve? Well, on the interval between -1 and 0, the top curve is the cubing function. Once you get beyond the origin, right, so from 0 to 1, the top curve changes, and now it's the identity function, y equals x. I point this out because if there's ever a change like this in the top curve and the bottom curve over an interval, it's going to require another integral. Okay, so in this case, two separate integrals to calculate the areas. Okay, so for the first rectangle, over the interval from -1 to 0, you know what, let's do it like this. Okay, and the length of that rectangle is the difference of the y coordinates times the width. And so this implies then that the area of that little sliver, that region, okay, and then we calculate that integral. Next, okay, in this case, right, for 0 to 1 now, the length of the rectangle, top curve minus the bottom curve, right, that's always in our minds. And so the area of that second region okay, now both integral, I'm sorry about that, gang. I got the powers out of order. There we go. Now, so what we do is we calculate both integrals. They are routine, right? You can read them off term by term, okay? So I'll leave that to you to figure them out. And then what you do is you combine them both. So I'm going to make a note here. Add these together, okay? So it seems pretty straightforward. Now, there's a way that we can get out of this without doing two integrals. Can you see it? Yeah, maybe what we can do is, since there's a symmetry to the regions, right? Maybe all we really have to do is find the area of one of the regions and double the result. Okay? That's a little bit smarter, right? We always think, gang, you want to work smarter, not harder. So maybe what we'll do is, I'm going to make a note. Okay, so when we go back and look at this later, we know what we were thinking. I'm going to use symmetry and say that the total area okay, and then what I'll do is I'll just simply choose one of these two integrals above. It doesn't make a difference which one you choose, but pick one and double the result. Okay, let's calculate the result. Okay, all right. Next example. Okay, so we want to find the area. So the first one, if you remember from your pre-calculus days, right? The first equation, that's going to be a parabola. It's going to open sideways. The second one is the identity function, y equals x. Okay, so there's our identity function. Okay, the second one is a parabola. And it's going to look like that. Okay, now I'll leave it to you to verify, gang, that the two graphs intersect each other. At those 2 points. Sorry about that. Okay. All right, remember, you can find that by setting both equations equal to each other and then solving. All right, so the area that we're interested in is this stuff right here. Okay, now, we have to be careful here, right? Because just like with the last example, we always keep in the back of our minds top curve minus the bottom curve. But again, here's the thing. The top curve here is the positive square root of 12 minus 4x, okay? And it stays that way until you get to the vertex right there. The bottom portion is the negative square root, okay? So why does that matter? Because notice that if you read the shaded region from left to right, starting here, notice that the top curve is the green line and the bottom curve is the negative square root. But once you get to the next intersection point, okay, and what I'll do is I'll put a red division line there for a moment, okay? Notice now that the area to the right of that little red line is going to have a different top curve and bottom curve than the shaded region that came before it. Now, remember what that means, right? We said that when there's a change in the top and or the bottom curve, then it's going to require separate integrals. So now we're looking at two integrals. And that's okay, that's fine. But remember we said just a few minutes ago that we would prefer to work smarter, not harder. All right, so here's what I propose. Let's make a little bit of room. And the differential element of area is going to be turned sideways. Okay, so what I'll do is I'll take some generic y value. Okay, think up and down now, say maybe right about here. Okay, and the rectangle that corresponds to it is now this. Okay, so we're using a sideways differential element of area. It was a little sloppy. Okay, and now what I'm going to do is I'm going to label both sides or both ends of the rectangle the way we've done before. Okay, so notice that both ends have the same y coordinate. The green line is x equals y. The blue curve is x equals what? Yeah, see, we can get that from here, right here. Okay, so that's what's going to go right here. Okay, now in this regard, gang, think right minus left. Okay, that is to say right curve minus left curve. So when the very thin rectangle is vertical, we think top curve minus bottom curve. But if we switch it sideways, then we think right curve minus left curve. Here's the area of that thin rectangle. First of all, its length. What's the length of this rectangle? Now it's horizontal. So it's going to be the difference of the y coordinates. Times the width of that rectangle. Okay? It's clever, isn't it? So the total area is going to equal the sum of all of those elements as they range from y equals -6 to y equals +2, and all of those elements have this form. Okay, now after that, it's going to be straightforward calculation. So maybe we'll just go a little bit further, and then I'll have you take over. Okay? All right, so we have y equals the sine of x. Y equals the cosine of x. And we want to find the area shaded in this part right here. Okay, so to that end, we're going to need the intersection points. So it looks like they're going to intersect where? Good, pi over 4. What's the next one? Yeah, good. Okay, good, 5 pi over 4. So now we'll put our thin rectangle somewhere between pi over 4 and 5 pi over 4. Say maybe here. Okay, and then we'll label the top and the bottom of it like we always do. Then find the area of that differential element. Okay, remember it's a rectangle, so length times width. And so the total area will equal the sum of all those elements as they range from pi over 4 to 5 pi over 4. Okay, and then again, routine calculation. Okay, routine calculation. So I'll leave that to you to figure. Okay, so here we have a diagonal line. Okay, and then we want to find this area. okay? Now they're all diagonal lines, gang, so you can find the equations of all these lines, and that's fine. But let me just point out, notice that from 2 to 4, the top curve is the black line, and the bottom curve is the blue line, okay? So there's the top, and there's the bottom. But once you get beyond the 4, so from 4 to 6, the bottom curve changes. It's a completely different diagonal line. Remember, always remember, if there's a change in the top and or the bottom curve, it's going to require a separate integral. So we're looking at using 2 integrals to find this shaded region right now. On the other hand, it is a geometric shape we recognize, okay? It is a triangle. We could probably find the area using trigonometry. Let's try something else. Okay, what's a way that we can find the area of this triangle without using calculus or trigonometry for that matter? Well, there's probably a few ways you might be thinking of right now. For example, we could do this. Okay, drop a perpendicular here and here. Now what that does is it creates 2 right triangles, there and there. The overall shape we just created is a trapezoid. If we could find the area of the entire trapezoid and then subtract out the 2 green triangles, then we would have our result. Okay, so it would be area of a trapezoid minus the sum of the areas of the 2 right triangles. Okay, and no calculus would be required. We get all the information we need from the grid right here. Can you think of another way? Yeah, good. Maybe you were thinking connect this right here and have one larger triangle. You can do it that way as well. Okay, here's another alternative. Okay, make one large rectangle. Okay, one large rectangle, and then find the areas of the 3 right triangles, these 3 green ones right here, this one, and this one. Okay, so one large rectangle, find its area, and then subtract out the sum of the 3 right triangles. So you can do it that way as well. And so these are ways that you can, I mean, the integration is fine, gang. Calculus is good. But if it isn't necessary, remember, always remember, work smarter, not harder. If an opportunity like that presents itself, you should take it.